Welcome to Derivability. Today we're going to be looking at velocity and acceleration in polar coordinates. This is something that's very common for a maybe sophomore, junior level mechanical engineering physics major. Okay, uses some good trig and calculus stuff. I don't think you see this in a calculus class, although it's a very good application of the chain rule and other things that you are ordinarily interested in calculus. Okay, so before we get to what is more like the meat and potatoes of the video, let's just do a little prep work here. The diagram hopefully is a helpful setup. Okay, so I have a position vector r angled at some angle theta relative to the positive x-axis. Okay, and at the tip of that position vector in green, I have the usual good old ij unit vectors. Okay, but we also want to imagine polar unit vectors, which I'm calling u sub r, u sub theta, using the hat notation on top to denote unit vectors. Okay. The trick here, you might say, is that the ij unit vectors are constant in direction. Okay, no matter where you are in your coordinate system, I always points to the right, j always points up. Okay, not so with the polar unit vectors, u sub r, u sub theta. Okay, you can see here that they're kind of inclined at the same angle, theta, that the position vector r is. Okay, you can see that I've tried to draw some little blue arcs here, denoting the angle that those vectors make with respect to I and j, that is with respect to the usual x and y directions. It's the same as, you can probably figure out, same as this angle theta back here. Okay, so our first task is to write u sub r and u sub theta in terms of the I and j unit vectors. Okay, and this is just like writing any other vector in terms of its components, in terms of I and j. Okay, so little triangle up here on the upper right side of your screen right now. So we can see here that this x component of u sub r, okay, is going to be cosine theta, and this points in the I direction. Okay, the y component, sine theta, points in the j direction. Okay, so u sub r we can write as cosine theta I plus sine theta j. Okay, we can do something very similar for the theta unit vector. Okay. All right, so once again, we have an angle theta right there. Oops, it would look a little bit better if it were an arc. There you go. Okay, so the vector is u sub theta. All right, and I'll let you kind of fill in the sides of the triangle if you want to here. But what we're going to get is u sub theta equals minus sine theta I plus cosine theta j. Okay. All right, a little bit of prep work here. The magic, you might say, is going to happen when we consider the derivatives of these unit vectors. Okay, you might be saying, well, what do you mean? Well, I and j don't have, their derivatives are zero. They're constant in magnitude unit vectors, constant in direction. Okay, the r and theta unit vectors are constant in magnitude, that's true, but they are not constant in direction, and that will factor in. Okay, so let me create some more space down below, and we'll resume in a moment. Okay, well, let's get back to it here. All right, so I've recopied the u sub r, u sub theta, and they look like functions of theta. So, let's just kind of follow our nose, so to speak, and take derivatives of these with respect to theta. So derivative d u sub r d theta, okay, it's not going to be super difficult, minus sine theta I plus cosine theta j, and du sub theta with respect to theta. Okay, that equals minus cosine theta I minus sine theta j. Okay, all right, so what big deal? All right, well, just take a close look at these. And I believe we are going to see here that the derivative of u sub r with respect to theta is exactly the unit vector u sub theta. Okay, and the derivative of u sub theta with respect to theta, apart from a minus sign that we can distribute out, is equal to u sub r. Okay, so we can write this as minus u sub r. Okay. Now, in terms of motion, velocity, acceleration, we're not interested in derivatives with respect to theta. We're interested in derivatives with respect to time. Okay. Well, that's not a real big deal. That's the chain rule here. So, for instance, here in a moment, we will need to do du sub r by d time. Well, that's going to be du sub r by d theta times d theta by dt, chain rule. Okay, all right, so from this we get u sub theta, and then that derivative with respect to time, just kind of a shortcut, we use what's called dot notation. Okay, and then d u sub theta with respect to time, kind of very similar here. That's du sub theta with respect to theta, and then d theta with respect to time. Okay, and as we decided before, that's minus u sub r, and then we have a factor of theta dot. Okay, all right, so now we are ready to start working on the velocity acceleration components in these plane polar coordinates. Okay, so what we're going to start off with is talking about the position vector r having a magnitude r, and it always points in the radial direction. Okay, there is no theta component. Okay, that will come up here soon. All right, so to get the velocity, what we want to do is take the derivative of the position with respect to time. Okay, so that's going to be r dot u sub r. Okay, but we have a product here. Let's use the product rule. Okay, so you recognize the product rule, most certainly. Okay, so r dot u sub r plus r times du sub r by dt. Okay, the reason this happens here, whereas it does not happen in Cartesian coordinates, is that the Cartesian unit vectors are constant in terms of direction. U sub r is not. So we have to take its derivative, which we've done some prep work on. So we have r dot u sub r plus r, and then du sub r with respect to time, okay, is going to be theta dot times u sub theta. Okay, all right, and before we've really gotten very far here, almost looks like magic at this point, we have figured out what these velocity components are in polar coordinates. So v sub r is r dot, and v sub theta is r theta dot. Okay, in other words, we have v sub r times u sub r plus v sub theta times u sub theta. Okay, in maybe a first semester physics, you might be more familiar with talking about v sub theta as something like called a tangential velocity. Often we write it as r omega. Okay, so maybe a few things from a previous class coming back to you here. Okay, now basically we're just going to wash, rinse, and repeat to get the acceleration vector components. Okay, so I'll create a little bit more space, and then we'll get right to that. Okay, we're back now. And so we have, as we said before, v equals r dot u sub r plus r theta dot u sub theta. And we're just going to kind of, keep on going here. Acceleration vector, that's dv by dt. Okay, let's just keep on going with our product rule, chain rule, what have you here. So first term, product rule, I'm going to do r double dot u sub r plus r dot. Okay, now we've kind of been through this once or twice now, so the derivative of u sub r here is going to be theta dot times u sub theta. Okay, all right, so that's our product rule on that first term. Now for the second term here, I've got three things, r, theta dot, and u sub theta. So product rule is going to contain three terms. Okay, so it's going to be an r dot, theta dot, u sub theta, plus r, theta double dot, u sub theta, plus r theta dot. Now the derivative of u sub theta is minus theta dot u sub r. Okay, now all we need to do now is group like terms. Okay, so I've got two terms that are attached to a u sub r unit vector. Okay, so if I group those together, I'm going to get r double dot minus r theta dot squared, okay, all times u sub r, okay, plus, let's do the same thing for u sub theta. Okay, let me start with this term. So that's r theta double dot. Okay, and then notice that these two terms are identical once you remove the parentheses. So we get plus 2 r dot theta dot, okay, and then all of that times u sub theta. Okay, so what we do here is we identify a sub r, r double dot minus r theta dot squared, and a sub theta as r theta double dot plus 2r dot theta dot. Okay. Now some of this is familiar, some of it is maybe not so much. Okay. In a sub theta, the r theta double dot term might remind you of something like an r alpha, alpha being angular acceleration, maybe from first semester physics. That we sometimes call tangential acceleration. Okay, going back over to a sub r, this r theta dot squared actually can kind of be rewritten as v sub theta squared over r. Okay, and that should immediately remind you of a centripetal acceleration. Okay, it points inward. All right, that's the negative sign there, and that's aligned in the radial direction. So it's appropriate that that belongs with a sub r. Okay, something that might be new to you is this last term in a sub theta. Sometimes this is called the Coriolis term. Okay, and you will encounter this again in your dynamics, mechanical engineering, when it comes to maybe accelerated rotating coordinate systems. Okay, but this is basically, you know, maybe getting a little ahead of things, has to do with conservation of angular momentum and how an object tends to speed up or slow down in the angular direction when its radial coordinate changes. And again, the r dot in that term means the radial coordinate is changing. Okay. All right, so there you go. I hope this has been helpful. Maybe you're watching this before your class gets to this. Maybe a quick review. You know, after your professor has gone over this, or maybe your professor saving a little time skipped this. So hopefully seeing all the steps is very helpful. Thanks for dropping in today. Would appreciate it if you you know, like, subscribe, share derivability with your friends and classmates, and hopefully we'll make a difference for you and your friends in your courses sometime soon.